Good afternoon, everyone. My name is Ruzbe Tehrani. I'm an assistant professor at Temple University in Philadelphia. Today, I have the pleasure to present the use of biological systems in my projects in remediation. Just last year, EPA turned 50 years old, and if you look on the timeline of events on your right, you can see that biological systems have been there much longer than us, taking care of the environment. So it is not surprising that we rely on biological systems to remediate our footprint. And when it comes to biomimetics, we do not need a fancy example in the medical field. We have been using the same concept in wastewater treatment facilities for more than a century. Now, considering the treatment of complex hazardous waste, I have always remember what we were told in grad school. Don't mix your hazardous waste. But what if you have to deal with a complex mixture? What if you have a high concentration of less important contaminant that is easily removed, but you have low concentration of a very toxic compound in the same mixture? Do you have any selectivity in your removal and treatments? So my question is, what if I have to treat a complex mixture? How can I offer selectivity in my treatments while reducing cost and the treatment time? So I thought about using nanoadsorbents and nanomaterial science. The literature is flooded with the use of nanoabsorbents for toxin removal. However, nanomaterials are not stable in aquatic systems. Once they're used, it is very costly to remove the exhausted adsorbents from the treatment system. Also, you do not want your nanoadsorbents to be released into the environment. So there are serious technical bottlenecks in using nanomaterials in real world. I looked for an answer to see if similar processes exist in biological systems. Indeed, biological systems use permeable membranes to contain carrier molecules. So here we use a membrane to contain our nanoadsorbents. And we relied on concentration and pressure gradients to move toxins from the hazardous waste side into the nanoadsorbents. And thus, on the opposite side of the hazardous waste mixture, a fluidized nanoadsorbent system continuously picked up the contaminants. And thus, we came up with dialysis systems that use nanoadsorbents to remove toxins selectively and faster. Here on your right, we compared the removal of lead in a regular dialysis system to a nano-enhanced dialysis system. As you can see, the addition of layered bernicide or manganese oxide allowed us to remove lead in a dialysis system much faster. And when it comes to mixtures, that allowed us to remove lead selectively. So what did we achieve here? We resolved the issue of aggregation of nanoadsorbents by continuous mixing. In this system, nanomaterials are always contained in a closed system. In contrast to batch reactors, here we do not worry about recovering the exhausted nanoadsorbents. If you are to remediate a mixture of contaminants, but you're solely interested in removing one or two of the toxins due to cost or regulatory issues, our proposed solution allows you selectivity for that mixture. Here we can mix and match nanoadsorbents based on the toxins of your interest. In the proposed approach, not only we are offering selectivity, we are also continuously recirculating the nanoadsorbents. So if they're expensive, we recirculate the nanoadsorbents till they are fully exhausted. Another biological system that I would like to bring to your attention is the old phytoremediation, a field that has been investigated significantly for decades. Among the remediation community, phytoextraction has not been well received for many due to efficacy in the field, typically blamed for slow growth or feasibility. But more importantly, the biggest problem is the management of the contaminated biomass once the treatment is completed. So now the question is, what do we do with the biomass once it contains toxins and their metabolites? What I propose is the use of simple indigenous plants that are not only hyperaccumulator of ions, and I'm saying hyperaccumulator of ions, not just metals, and toxins, but also very resilient and easy to maintain and process. For example, we have been using aquatic hyperaccumulators to regulate ionic concentration, pH, salinity, and of course, toxin removal. Tolerance of these plants to harsh environments such as high salinity, extreme acidity is mind-boggling. But what is more important is that these plants can be used to regulate pH, salinity, adjust ionic strength, and of course, toxin removal. Whenever I talk about this project, I always joke that we have been really trying hard to destroy this plant, but it has survived us. Here we demonstrate a few examples of the use of these hyperaccumulator aquatic plants in our projects, regulating pH and ionic strength. Once we are done with the remediation, we still have to answer the question we asked earlier. What do we do with the plant biomass? Our suggestion is that we use simple indigenous plants that do not have complex structures in the beginning, where shoots and roots are processed similarly and no physical separation processes are needed after remediation. We also suggest the use of controlled pyrolysis, which has been optimized, instead of incineration. Under controlled optimized pyrolysis techniques, we have been able to reduce the biomass significantly, but more interestingly, we have been able to generate new composites, new materials. Sustainable production of graphite and graphene has received a lot of attention these days. Here are contaminated biomass, of course, depending on the elemental composition and toxicity, could be used for the discovery of new materials, specifically composites, after controlled pyrolysis. Here in this project, our aim was to capture indium, a strategic element from electronic waste. We were able to accumulate high concentrations of indium in the plant biomass from even, and consequently we were able to make new graphitic indium composite with certain properties that were fit for sensing and possibly capacitors. So your waste could be our treasure. We have been using plant biomass for various applications after remediation. Here we have the minimum use of chemical and energy in processing our new nanocomposites. While we are aiming to remove toxins, remediate our footprint, and at the end generate new materials, also remember that we are capturing carbon dioxide. Here you can see a TM image of one of our layered nanocomposites generated from plant biomass after remediation. This nanocomposite is very similar to graphite. However, our biomass is doped with elements depending on the site that we have done the remediation. Now, with the minimum use of chemicals and energy using biological systems, we have been developing new materials that have never been synthesized and never been tested for batteries, sensors, capacitors. Again, your field contaminants could be our treasure. I will be more than happy to know what's happening in the field, what materials you're dealing with, and what are the possibilities that we could develop new materials from the biomass that we gain from the remediation of the site. Last but not least, I appreciate my student hard work to make these projects possible. Here, I share two examples of projects using biological systems in remediation. One was inspired by biological system for the use of nanomaterials in remediation of complex hazardous waste. Here, we can offer selectivity in removal. The second example was to resolve the bottleneck of remediation. Management of contaminated biomass could use less energy intensive processes to reduce the biomass and generate new materials. I appreciate your kind attention and I will be more than happy to answer your questions.